Hi Arvind, how are you? Arvind? Arvind, are you able to hear me? Hi Arvind, you're able to hear me?
Hello, sir.
Is it audible? Can you hear me, Arvind?
Okay, sir.
Okay.
Hello.
Okay, we'll start today's session.
Sir.
In today's class, Global Positioning System, I'm going to discuss on the issues that are being dealt with the coordinate systems, the reference system of conventional celestial type, conventional terrestrial type, time systems, different timing zones, the Keplerian format, which has three different subsections: Keplerian orbit, Keplerian parameters, and the Keplerian elements, followed by perturbed satellite motion with disturbing accelerations and satellite visibility and topocentric motion. So all this comprises your unit number 2, and all these things we'll discuss in today's session. So if anybody is late to the class, no issues, let them join lately also. The video is recorded. Probably I think so. Let me check. So the lecture is being recorded. So those who are coming late, I'll share it to them such that they can understand in a better way at a later time. Okay. So moving on to the coordinate system. So the coordinate system is that the oscillation of with respect to the initial space, which we call it as nutation. So how do we get this coordinate system is that for positioning any object or positioning any celestial body on earth or in space or in satellite, three important coordinates are required, as we had seen: a latitude, longitude, and altitude. So in that there will be an oscillation of some period which we determine it as omega. So the oscillation of this omega with respect to an initial space, we call it as nutation. So which is the effect of partitioning into secular precision and periodic nutation. So the oscillations could be with respect to terrestrial, and it is named as polar motion. Oscillations, movement of objects or celestial bodies. And if the image position of this omega is denoted by P, we take a polar plot of that and we place it. So the free oscillation always results in a motion of a rotational axis. You can see in this diagram a rotational axis along a circular cone. So we will determine it as a circular cone, which means that the mean position as axis and an aperture angle of 0.4 degrees is present. Always this has to be considered of 0.4 inches. So on the earth, the motion is represented by a distance of 6 meters radius circle along P. So we can have a maximum oscillation up to 6-meter radius. So if I consider P is the point, mean position of the point on the plotting of polar plot, so it can have up to an oscillations of approximately 6 meters of radius circle. So this positioning of free oscillating Earth's rotation can be denoted by R naught. For example, if I want to find it for a point of R, so we can take it from 0.5. So R naught is the Earth's rotational axis, which is approximately taking the 0.5 meters, and the period of free motion around this will amount to 430 days. So a period of free motion constitutes about 430 days for this periodical rotation, which we call it as calendar period. So this is your calendar period. So calendar period will have a rotation of about 430 days. So 430 days is equal to one calendar period. So this is how we determine it. So the forced motion is described by a cone mapping by a circle around a free positioning, and the radius of this circle can be related to a tidal deformation of approximately 0.5 meter. So I had said here we have 0.5 meter. So this is your tidal deformation or an appropriate information. So we have a period of forced motion corresponding to terrestrial part of the tidal potential of some degree level, and this will be having a momentum axis within 0.001 of the rotational axis, with an angular momental axis being forced by the tidal attractions. So the free polar motion will be always being fixed as m is equal to 0, and the results of this coordinate with the tidal deformation is implied by the law of conservation of angular momentum. We need to take the law of conservation of angular momentum, and this will exist as long as there are no external forces being applied. So the mentioned above properties appropriately serve as a reference axis, and the scientific community which is being determining its free position is by space celestial ephemeris pole, CEP we call in short as CEP. So this coordinate system serves as a reference axis in the terrestrial, where the mean position of the rotational axis denoted by P is called conventional international origin. I'll show you that. So this P which we have done is the conventional international origin. So this is your position of that object. So by convention, the x-axis is identical. So we have two methods after this conventional. After we have defined this conventional international origin, we have two reference systems with which reference we are going to take this. One is conventional celestial reference system. Another one is, let me show you, conventional terrestrial reference systems. So these two reference systems lies as a basic fundamental with respect to this P. So which can determine our coordinate systems information. So in the celestial reference system, we'll be using celestial reference frames. So this celestial reference frames have been determined by an equinox. So what is this equinox? Equinox is defined as a set of fundamental stars with conventional and practical realization that do not require any coincidence with the theoretical concepts. So we call it as a conventional. So this equinox is being obtained by the identical position of the angular momentum axis at a standard approach. And this gives a point called quasi-inertial point. So the quasi-inertial point is always added to a point that the geocentric system doesn't have rigorous inertia. Why? Because the accelerated motion of the Earth around the Sun is always not rigorous. So we take quasi-inertial scheme. So one example of such a celestial reference system is the IERS, International Earth Rotational Service. So this is called as ICRF also, International Celestial Reference Frame System, where the first letter indicates IERS, International Earth Rotational Service. So this is given by kinematical system, which can determine over 500 extragalactic objects, mostly galactic nuclei or mostly quasars in space. Next comes the terrestrial reference system. So this terrestrial reference system is always present on the Earth's surface. So where the mean position of the Earth's rotational axis is present, and we have an X1 axis which is associated with the mean Greenwich meridian time. So we call short it as GMT time. So with that, it is being associated Greenwich meridian time, which is the exact center location of the Earth's sphere. So that time determination is always GMT plus 0, plus or minus 0. We don't have any other reference for that. GMT, Greenwich meridian time. And this system is called as the terrestrial reference frame, with a set of terrestrial control stations serving as different reference points. So most of the reference stations are equipped with satellite laser ranging, SLR, or very long baseline interferometry, VLBI capabilities. So these stations are equipped with this ranges for determining the positioning. So these are being realized by number of terrestrial satellites, where plate tectonics, tidal effects are being regularly updated and supplemented to the last two digits of the last year. For example, uh, last year they are determining the platelets information or some tidal effects. Tidal effects like wind, power source, sunlight, all those things. All those are being realized by the terrestrial sites. So the last two digits are meant for always updation. So today, if the last two digits are 01, in the next year it will be updated to 02, and so on, depending upon the positioning. And these are some of the parameters which describes or which are being given for a celestial terrestrial reference system. Conventional terrestrial reference system. So A value can be in this range, 6,000. Oh no, it's okay. 63 lakh 78,137 meters. So what is this A value? Is that it's the semi-major axis of the ellipsoid, and the flattening of the ellipsoid F should be always 1 divided by 298.257223563, and omega E should be omega E represents the angular velocity of the Earth, so that should be always 7292115 point. Oh, sorry, 15 into 10 power minus 11 radians per second, and always the Earth's gravitational force is this one, 3986004.418 into 10 power 8 meter per cube per second square. All this determines this positioning. Okay, for this. So this is about the coordinate systems and the reference systems. In the next topic, we are going to see about time systems with respect to GMTs. All references are taken with respect to Greenwich. Sorry for that. Greenwich meridian time. We call it as GMT. So solar and sidereal times is the topic, and we have dynamic times, atomic times, GPS times. So these are the four. So first let us see solar and sidereal times. So a measure of Earth's rotation is the hour angle, which is the angle between meridian of a celestial body and a reference meridian, which we call it as Greenwich meridian. So a measure of Earth's rotation is the hour angle, which is the angle between meridian of a celestial body in space or in motion, which is stationary or in motion, and a reference medium. So next we have universal time, UT we call it as. UT is defined by Greenwich hour angle augmented by 12 hours. So 12 hours of fictitious sun uniformly orbiting an equatorial plane. The 12 hours is a universal time. Sidereal time is defined by the hour angle of vernal equinox. So taking the mean equinox as the reference leads to mean sidereal time, and using the true equinox as a reference that yields true or apparent sidereal time. So this equinox is being determined by this celestial reference system, which uses your triangular laws of triangulation for determining the positioning. Sidereal time. So both this solar and sidereal time are not uniform. Why? Because the angular velocity is not at all constant. So they cannot be uniform at all, solar and sidereal. So there will be fluctuations slightly or largely due to the changes in the polar moment of inertia, due to the tidal deformation, as well as other mass transportation or movement. So there will be an variation. So it will be always non-uniform. And another factor that determines this is that the oscillations of Earth's rotational axis itself. So the Earth rotates in its own axis. So that also plays a major role in non-uniformity of solar and sidereal times. So then they had gone for using dynamic times. The time systems derived from planetary motions in solar system are called dynamic times. Derived from planetary motions. Movement of the other planets with respect to Earth was determined. So that we call as dynamic times. There are barycentric dynamic time, which is used as an inertial time system in Newtonian sense, providing time variable in equations of motion. So that is the first type in dynamic times. Another one is the quasi-inertial terrestrial dynamic time, which was formed from ephemeris time in order to determine the motion of orbital motions of satellites around the Earth's surface or around the Earth. So that was the second dynamic time. And third one is the International Astronomical Union, IAU, which was introduced as a term TT, TT, to replace terrestrial dynamic time. The terrestrial time is being given by International Astronomical Union. So instead of TDT, they had introduced this terrestrial time. It's just the renaming of that. Okay. So next, coming to the atomic times. In practice, the dynamic time system was achieved by using some atomic time scales. So for that, UTC was a very promisable universal time code. It was a very promisable timing system. The unit of the system was in atomic seconds. It was very kept close to UTI, and approximate civil time integer leap seconds were inserted at distinct apertures. So this GPS time was introduced as your next case by the US Naval Observatory, US United States Naval Observatory, USNO. which had a constant offset of which had a constant offset of having 19 seconds with IAT system, and which coincided the UTC system, universal time. So which was given in during the year 1980. So this GPS time was was being introduced as a overcome of all these solar, dynamic, atomic, and this had control segments with high accuracy, cesium beam atomic clocks, both at central clock station and at the remote monitor station. This had clocks consisting of high accurate GPS time, to which the satellite clocks time are being compared, corrected if required, and uploaded by commands to the satellite. So the GPS satellites carry redundant cesium and rubidium atomic clocks, such that if the UTC fails, GPS can overcome on that. One marked difference is that GPS time does not introduce any leap seconds. So for that, they'll be using the GPS P or Y code receivers for maintaining the constant time of the satellite. So this leap seconds is cannot be introduced in GPS, since these leap seconds will lead to computational timing errors. So leap seconds are being avoided in GPS by these P and Y code receiver system. So, however, this leap second effect will have an attempt on control segment of GPS with 1 microsecond. Okay, just 1 microsecond of delay can be obtained by using this GPS time with respect to UTC, so which can be negotiated. So always the GPS time will give us more accurate time standards. So this is being adopted by the United States National Observatory. Sorry, Naval Observatory. Okay. Navy systems. So they had introduced that, which had 1 minute, 1 microsecond of leap seconds. Then moving on to the next topic is the Keplerian orbit. So this Keplerian orbit is being obtained by the laws of satellite motion in space, which is being guided by Keplerian's law. So the Kepler's law states that all the satellites that are being placed above the Earth's surface from a distance of about 36,000 kilometers all will follow a path of ellipsoidal elliptical path, such as it reaches the space designated space location. So that should satisfy Keplerian motion and Keplerian orbits. So about the Keplerian motion or the Keplerian laws, you will be studying in detail in satellite communication, where the launch of a satellite will play a major role. So how do we launch? What are the prerequisites and conditions? There Keplerian law plays a major role. So assume that there are two masses, m1 and m2, separated by distance r. Consider that the moment only consider for a moment that only the attractive force between the masses, and applying Newton mechanics, the moment of mass m2 is relative to m1, defined by homogeneous differential equation of second order. So we have a time denoted by inertial time provided by GPS system. So in case if the motion of the artificial Earth satellite is being considered, so then we can neglect the body's point masses, and we can write the equation as this: G which is a universal gravitational constant, mass of 2 points m1 plus m2 divided by r cube into r is equal to 0. So what is this r? Is that relative position of the object with respect to that location. And what is this r double dot? Is a relative acceleration. So which is differentiation of this r. So dou square r divided by dou, with respect to time acceleration. So dou square r divided by dou t square. Keplerian motion. There are 6 parameters of Keplerian orbital motion which determines the satellite's positioning. One is right ascension of ascending node, which is denoted by this parameter, one symbol. Second one, inclination of orbital plane, which is denoted by I symbol, is this I. Another one is argument of perigee. I'll tell you what is this. Perigee is semi-major axis of orbital ellipse, alpha. Numerical eccentricity of ellipse, which is E, and apogee of perigee passage, which is T naught. So all these are the 6 main parameters. 3, 4, 5, 6. 6 Keplerian parameters that are to be satisfied by any satellites. So consider this is the point, the center is the point. From here we are placing a satellite in space at a minimum distance of 36,000 kilometers from the Earth's surface. We have 3 planes, X plane, Y plane and Z plane. F is the field or frequency that we have seen, the small f. So where the flattening of the ellipsoid is being determined by 1 over 298.25722353, and A, which is a semi-major axis of the ellipsoid, is being considered. So 2 factors. Then we have the omega. We draw an reference line which is perpendicular to the satellite's positioning. The angle difference is taken as omega, and this difference is f. This angle difference is right ascension of ascending node, and we can calculate all these things. One is mean value, second one eccentric value, another is the true value by using Keplerian orbital parameters. So I had said you about perigee, and we have another concept called apogee also. I think most of you are familiar with apogee. So what are these apogee and perigee are? Is that the closest approach of the sun, sorry, of the satellite, not the sun, the closest approach of the satellite with respect to Earth's center of mass is called as perigee. The closest point of satellite and Earth is perigee, and the most distant point of the satellite with respect to Earth center is called as apogee. Closest distance perigee, longest distance is apogee. So with this, the closest distance of the point will be determining the approach. So this is what argument of perigee and approach of perigee passage. Then the intersection between the equatorial and orbital plane with the unit sphere is termed as nodes, where the ascending node defines the northward crossing of equator. So wherever we move towards north, the crossing of equator occurs. So that point we call it as nodes. And we have a relation for that. How to find that? Which is given by Kepler's third law. So Kepler's third law gives you n is equal to 2 pi by p, and p is the position, so which can be elaborated as square root of mu divided by a cube. So where A value is about 26,560 kilometers, the nominal semi-major axis of the ellipsoid, which is being orbiting over 12 sidereal hours. So n is your satellite's velocity, mean angular satellite's velocity. P is the revolution period. So it you have seen. So we assume that in orbit with semi-orbital period having an eccentricity 0.1 at an approach 3 hours after perigee passing gives you a mean of 90 degrees. So the calculation of the eccentricity requires iteration and gives value around 95 degrees. So which is this? How to calculate? So how to calculate the mean is n of t minus t naught, and e of t is equal to m of t plus eccentricity sine e of t, where v of t, which is your true value, can be obtained by 2 arc tangential square root of 1 plus e divided by 1 minus e tangential e of t by 2. So we'll see that what are the Kepler elements. There are 6 Kepler elements as already stated, which are used to describe the position of satellites in space. For normal orbits, the satellites move in orbital plane, which is always fixed, and the actual path of the satellite in the orbital plane is an ellipse. Strictly, it's always ellipse, and one has to consider the following orbital ellipse conditions for determining the orbital motion. One is treating the Earth as a point mass or equally as a sphere with a spherically symmetric destiny distribution, and considering that the field of gravitation is always radially symmetric, so that is all the plumb lines are all straight lines and points towards the center of sphere. All the straight lines and plumb lines should focus towards the center of the sphere for considering the mass, for considering the Earth's point mass. Second one is that the mass of the satellite is negligible compared to the mass of the Earth. You may send an about the satellite size or weight of the satellite size, weight as 15 kg, 100 kg, 200 kg, 300 kg. So as compared to the mass of the Earth, it is very negligible. So we have to consider that. Then you have to consider the motion of the satellite, that it takes place in a vacuum, which means that there is no atmospheric drag acting on the satellite, or there is no solar radiation pressure. And we also consider that no other celestial body, neither sun nor moon, gives us gravitational attraction on the satellite. So all these 4 points has to be considered when determining the orbital ellipse for a simple orbital motion of the satellite. So moving on to the next topic is an important concept called perturbed satellite motion. So I'll give you 2 or 3 minutes for viewing these Kepler elements. So these Kepler elements are most important. Without the Kepler elements, we cannot determine any orbital motion such that the satellite's exact position or location cannot be determined, which will not give us values of that celestial body or the object which we want to determine. So I'll give you 2 or 3 minutes for viewing this, then I'll go for the next topic. moving on to the next topic, perturbed satellite motion. So this perturbed satellite motion is partial moving of your satellites, so which are being occurring due to the disturbed forces. So the disturbed forces will always cause the satellites to deviate from its simple or appropriate normal orbit. So when the satellite is moving in a particular orbit, due to this external forces, the satellite's motion will be disturbed. So which we call it as perturbed satellite motion. So the disturbances occur from non-sphericity of gravitational potential. Always the satellite will not go in a spherical shape. The attraction of the sun, moon, solar radiation pressure, and some other forces acting on the satellites uh, is a major factor. And there is another force called albedo, which is an force due to electromagnetic radiation reflected by the Earth, given by the sun. So then there will be a thermal radiation forces caused by this we have, which are very close to the Earth. There are several disturbing forces also, which can be computed. Particularly, the modeling has to be done. All the disturbing forces can be computed if they are very small, and the research on that is still going on. So, by knowing the accurate location of the satellites, we can treat the satellites' position coordinates by knowing the quantities of that satellite. And most probably, these applications, this type of applications can be used in GNSS, global navigation systems, which requires highest orbital accuracy, almost one centimeter level. So 1 centimeter level, this or that is being used. And however, for even surveying benefit from such accurate orbits, precision point positioning with a single receiver is most welcome. So the equations of motion would be expressed in an inertial or in a coordinate system corresponding to the approach of initial conditions, where x and x dot are the Keplerian elements, x comma x dot. You can see that how do we write x dot. So x dot can be given as the differential of x over, okay, and it goes on. Double x double dot will be differentiation with respect to time of this, and so on. So it will become x dx of dx by dt is equal to x dot, dx dot by dt is equal to minus mu x divided by x whole cube determinant plus x double dot g plus x double dot s plus x m dot x srp double dot, and so on goes on. So where the gravitational force field of the Earth can be determined by this x double dot g, dou r by dou x, dou r by dou y, dou r by dou z. These are x, y, z are the positioning and its transpose of that. So how do you calculate this r, which is your disturbing potential? R can be computed from this. Summation n is equal to 2 to infinity, m is equal to 0 to n, mu a exponential n divided by r power n plus 1, Pn cos theta into cos nm cos m lambda plus snm sin m lambda. So what is this Pnm cos theta? Is this which is obtained for gravitational field of the Earth, 1 minus cos square theta m by 2 divided by 2n into n factorial dn plus m divided by d cos theta n plus m cos square theta minus 1 into n. So where this can be approximated, this Pn bar can be also approximated as Pn bar is equal to square root of 2n plus 1 into Pn and the PNM bar can be obtained by n plus m the whole factorial divided by 2 into 2 plus 2n plus 1 into n minus m the whole factorial power minus 1 by 2 or square root of this into PNM. This is how we find gravitational field of the earth. We have another field component omega determined by minus mu by a cube square root of that ae divided by ae 1 minus e square eccentric the whole power square 3 by 2 j2 1 plus cos square I minus 1 minus 1.5 sine square I, and omega can be obtained by minus mu divided by a3 1 by 2 ae divided by a 1 minus e square the whole square 3 by 2 j2 cos I. So this is your impact of the gravitational field on the earth with the perigee and the nodal line referring to a data of a 26,600 kilometers. So this is the argument of perigee. This is your right ascension of ascending node with respect to motion degrees per day. Per day, how many degrees it has been inclined. Next is that acceleration due to sun and moon. The solar and lunar accelerations on the satellite can be given by this equation xm double dot. We would have seen that xm double dot as this. That motion due to sun and moon can be determined by this formula xm mu m divided by me xm minus m divided by determinant of xm minus x the whole cube minus xm by determinant xm the whole cube x xs is the acceleration due to sun, xm is due to moon. So where xs is equal to mu ms divided by me xs minus x divided by determinant of xs minus x the whole cube minus xx divided by determinant of xs the whole cube. So where the ratios of mm by me is always a constant 0.0123002 and the ms by me is 332 3000 sorry 3,32,946. So these are the expressions which were being determined by Plander and Plonick, their determination. So next is solar radiation pressure, which is this. We had found xg, which is due to gravitational. We had found xs, which is due to sun. We had found xm, which is due to moon. We are going to find next one is x SRP. SRP is your solar radiation pressure. So the solar radiation pressure is being obtained by the impact of light photons emitted from the sun on the satellite surface, where the basic parameters lies on the effective area, which is surface normal to incident radiation, the surface reflectivity, the thermal state of the surface, luminance of the sun, and the distance of the satellite from the sun. Computing all this SRP requires the evolution of surface integrals over illuminated regions, taking shadows of the radiations into account. Even if the regions are known, the evolution of surface integrals will become more complex due to the shape of your satellite. So for that, they had attempted two models. One is ROC 4 and ROC 42 models, which were used in Block 1, Block 2, and Block 2A satellites, respectively. Okay. So what is this SRP? Solar radiation pressure is that. So this is a diagram for that x-axis, y-axis, and z-axis, corresponding propagation along C. You can find the table also for C. Radial crossings. If z dash is the axis aligned with the antenna and points towards the center of the earth, The satellite finds its direction and remains locked it in with the help of an Earth limber sensor. Then X dash representing an axis which is positive towards the half plane having the sun. Y dash axis completes the right hand coordinate system and points along the solar panel axis. Then the satellites are oriented in such a way that Y dash remains perpendicular to Earth, satellite, and sun. The satellites will be oriented in Y dash. So here is Y dash, where they will be remain perpendicular to Earth, satellite, and sun. So the only motion of the spacecraft in this body fixed frame is the rotation of the solar panels. This will be fixed. These are your solar panels only that will be in rotating to make the surface of solar panels perpendicular to direction of the sun. So as the direction of the sun changes, this solar panel also will turn towards that in order to supply power to the satellite motion. So here we find the solar radiation pressure x double dot SRP, which is minus P. The minus P is the direction of motion of the sun, xn minus x divided by determinant of xn minus x plus y, xn into x divided by xn into x determinant. So the reason for its existence could be structural misalignments, thermal phenomena, thermal directions, misalignment of solar panels with the direction of solar photon flux. So here I will give you a list of perturbation on GPS satellites over a day. This was calculated for 1 day. So Earth flattening with a radial of 1335 gave along 1290 crossing of 6101. The total perturbation effect of 14,334 due to Earth's flattening. And due to moon's effect, 192 along radial, 1317 along the 361 cross, and totally 1379. And it's given for sun. What are the effects? By renowned historical satellite eclipse transit is the orbital determination, which is further complicated when satellites travel through the Earth shadow region. We call it as eclipse. When the satellite goes into eclipse region, what will happen or how do we determine that is a big question mark. So for that, so if just a minute. If an eclipse occurs, so which will always occur twice per year, every year two eclipse will occur when either the sun is in near the orbital plane. So then I'll show you two regions. One we call it as umbra region and next is the penumbra region. So there are two regions occurring due to this, which is the umbra is the portion of the shadowed cone that no light from the sun can reach, and the penumbra is the region of partial shadowing, which is that it surrounds the umbra cone. So while the satellite transits through the shadow regions, the solar radiation force acting on the satellite will be 0, which we call as umbra, or it will be changing, which we call as penumbra. Umbra and penumbra. I'll show you that in the diagram. So when the satellite is moving in a path, so it is going, so and suddenly an eclipse occurs. So the eclipse makes that the portion of the satellite is being covered. So this region is called as umbra, and a cone type structure which covers this region is called as penumbra. This occurs due to eclipse. So these changes in force must be taken into consideration in determining precise orbital computations. So in addition to this, there will be thermal radiation forces also, which gives the temperature variations. And the GPS satellites move through the shadow region in less than 60 minutes. Less than 60 minutes twice per day. So then the shadow region causes an additional problem, a precise orbit determination. So for that we need to go for ACS system of solar panel sensoring, which is called as altitude. It's altitude, not altitude. It's altitude control system, which have been mounted on solar panels exclusively for precise orbit determination, such that the umbra region or the penumbra region doesn't is being covered on that. The condition that the z-axis continuously points towards the center of the earth and solar panels are continuously normal to the satellite sun direction, that is the around the z-axis, in addition to rotating the antennas around the y-axis. So as the satellite passes through the shadow region, the ACS solar sensors do not receive sunlight and therefore cannot maintain the exact alignment of solar panels. But the satellite starts moving in some unpredictable way, which may cause Yan errors. In GPS observations in two ways. First is that the range correction from the center of the satellite antenna to the satellite center of mass becomes uncertain. The range correction of the satellite antenna and the satellite's mass becomes uncertain. And second is that there will be an unknown wind-up error. So these are the two Yan errors being occurred on in GPS observations. So this is your Earth shadow region, as I shown you earlier, umbra region, penumbra region. This Yan maneuvers or the Yan errors are occurred during surveying if the ACR solar cells do not receive sunlight, in that case only, which can be minimized by having some backups. So next topic is the disturbing accelerations. There are many disturbing accelerations that act on the satellite and that tend to make a big impact on the variations of Keplerian elements. One is the gravitational. Second one non-gravitational. So gravitational is that the non-sphericity of the earth and tidal attraction, either indirect or directly. The next is the non-gravitational solar radiation pressure, which is SRP, which is due to air drag, moment of wind, relativistic effects, solar wind magnetic forces, and so on. So considering all these things, we are going to determine what type of model can be used approximately or appropriately for maintaining this system correctly. Is that the subset of Earth model coefficients with WGS84. We'll be using WGS84, which is the Earth gravitational model determined in 1996, and it is recommended to use a subset of coefficients up to a degree level and order for 70 with high accuracy determination of orbits. So the non-sphericity of the Earth can be determined like this. So this is what we had seen in the previous. So there are some four effects which are being obtained due to this disturbing accelerations. First, we'll see the non-sphericity of the Earth. So the non-sphericity of the Earth has been determined by this: V is equal to mu by R, 1 minus summation n is equal to 2 to infinity AE divided by R whole power n Jn Pn into sine theta. So where lambda and eta are its latitude and longitude respectively, AE is the semi-major axis of the Earth, R is the geocentric distance of the satellite, Jn, here this Jn denotes the zonal coefficient of harmonic development from the Earth model, whereas Pn is the tesseract coefficients of the harmonic development known from the Earth model, and Pn, where somewhere I had seen Pn, yeah, Pn. Pn is the Legendre's polynomial, and Pnm, this Pnm is the associated legendary functions. So with legendary polynomials. Okay. So the first term on the right side, is this. Represents that is mu bar r represents the potential P naught for spherical Earth, and its gradient mu by r is equal to mu by r cube is considered as the central force for Keplerian motion. Hence, the disturbing potential R can be given by R is equal to V minus V naught. From this, we can obtain that. And we can show that the disturbing acceleration due to J2 is smaller by a factor of 10 power 4 than the acceleration due to V naught. Next is the tidal factors. The tidal factor is concerned with celestial body. Consider this: Earth is present, a satellite is present, and a celestial body in space is being moving. So the distance between the Earth and the satellite is taken as rho, and the distance between the satellite and the celestial body is taken as differential of rho, and we take a distance from the Earth to the satellite body as a value rho b. The angle being created between the celestial body with respect to the Earth and the Earth satellite to the Earth is z. We can easily determine the tidal effects. So the celestial bodies in the solar system can be a sun or a moon or a planet or any object that is to be evaluated by some analytical expressions of motion. So consider a celestial body with point masses mb and the geocentric position with this rho b, and the geocentric angle z between the celestial body and the satellite can be expressed as a function of rho b and rho, and the angle can be found out from cos z is equal to rho b divided by determinant rho b dot rho divided by determinant rho. Then we can find d differential of d rho double dot as gmb, which we call it as disturbing acceleration, can be obtained by rho b minus rho divided by determinant rho b minus rho the whole cube minus rho b divided by rho b the whole cube, okay, which is a disturbed acceleration for perturbed motion of satellites. Next, we are going to determine the solar radiation pressure due to this SRP. non-gravitational solar radiation pressure. So this was given by Schillinger during the year 1985. So where the perturbing acceleration is due to the direct solar radiation pressure, which will have two components. One is dp1 double dot and dp2 double dot. So where dp1 double is directed away from the sun and dp2 double dot is along the satellite. One is away from the sun, another one is along the satellite's axis. So there is an axis orthogonal to both the vector pointing to the sun and the antenna, which is normally directed towards the center of the earth. So usually we can find this SRP in terms of dp1, which is away from the sun, as V into K rho s square, rho minus rho s divided by determinant rho minus rho s the whole cube. So where rho s denotes the geocentric position of vector of the sun, K is a factor which depends on linearity of solar radiation term, which defines the reflective properties of the satellite and the area of mass ratio of the satellite. The quantity V is an eclipse factor, which is 0 always when the satellite is in shadow region, when the satellite falls in the Earth's shadow region. Therefore, this occurs twice a year for each satellite when the sun is in near the orbital plane. So when such eclipse lasts for more than 1 hour, always the eclipse will last for 1 hour. So this can be easily determined. So the eclipse factor equals 1 when the satellite is in sunlight, and for penumbra region the relation will be 0 less than V less than 1. This meaning is that in the penumbra region the satellite will have a V value in between 0 to 1, and the magnitude of dp1 will be in the order of 10 power minus 7 meter per second square. So hence the accurate model for factors k and v will be required, very much shorter than an arc. So this SRP, solar radiation pressure, is an extremely difficult to determine because the solar radiation term varies unpredictably over the year. It will vary, and a single factor for the reflective properties is not adequate for a satellites. So although the mass in the orbit is usually well known, the irregular shape of the satellite does not allow for an exact determination of the area to the mass ratio. And there is another problem in the modeling also, is that when the Earth's penumbra and the assignment of eclipse factor occurs, there will be a transition zone between the illumination and shadow. So there also we cannot get an appropriate uh, estimation. So the portion of the solar radiation pressure which is reflected from the Earth's surface also causes an effect called albedo, which we had seen earlier, albedo, which is due to Earth's ultramatic reflections. So then we have an effect called the last effect, relativistic effect. So this relativistic effect is based on the satellite's orbit that is caused by the gravity field of the Earth and gives rise to a perturbing acceleration which is given by d rho double dot, which is equal to minus 3 mu square a of 1 minus e square divided by c square rho divided by rho power 5. So where c is the velocity of light, which is approximately equal to 3 into 10 power 8 meter per second, and the perturbing accelerations will be given in the case of 3 into 10 power minus 10 meter per second square. So this effect is smaller compared to the indirect effects by the order magnitude which is to be determined easily. Coming to the next topic, satellite visibility and topocentric motion. This topocentric motion is being determined from the satellite visibility. So the topocentric motion of a satellite as seen by an observer on the surface of the earth can be computed from the existing expressions. So which is Lx is equal to xs minus xp. Xs is the geocentric position of the satellite in celestial coordinate system, whereas this position can be easily transformed into a fixed point coordinate system by xs. And we have another fixed point coordinate system at the ground, which is position of the observer on the ground in fixed coordinate, which is xp. So then the topocentric coordinate difference can be easily found as del x is equal to xs minus xp. Xs is the satellite's positioning, xp is the ground observer's position. So totally, the topocentric geodetic azimuth, elevation and distance of the satellite can be easily determined, and the geodetic latitude and longitude in these expressions can be computed from xp. Here it should be small p, xp small xp. So for lower accuracy applications such as creation of visibility charts, it is sufficient to use spherical approximations. Always we use spherical shaped structures. So this is about your satellite visibility and topocentric motion. These are the references. Any questions? And next week we'll be having a first internal test. For the first internal test, which is to be conducted in online, I had sent you a video usage of exam.net. So I request everyone to practice the exam.net. So the exam.net, I had kept opened my exam key code. If you have any doubts, you can refer the video. I'll send you a video once again today. Everyone has to upload the papers or upload or typeset in exam.net only. I'll share you again the video as how to write a test or how to use everyone practice how to write. I'll post it again in our class group. How to write exams online. Either you can typeset in the answer sheet, or you can write in paper, A4 sized paper, and appropriately you can upload within the stipulated time in exam.net. I'll be monitoring you for the entire duration of exam. I'll give you a tutorial video also. I'll post you the tutorial video. What are the do's and don'ts such that you can understand better practice within this week. And if you do any cheating or if you go for any malpracticing, that also can be easily identified. Just now I had posted in your WhatsApp group, in our class WhatsApp group for GPS learners. Check how you will be monitored. You can subscribe to the channel also for further videos that I'm going to upload you on these exams and GPS. The portion for internal 1 is only unit 1. Only unit 1 is the portion. And as far as assignment is considered, so many have them asked me, sir, still you haven't given me assignment. So today I will post you the assignments to each and every individual in Google Classroom. Everybody will be getting a unique topic. Which will be an application oriented. You need to find where this are being applied, or where do we find the applications of GPS. So that would be your major concern of assignment. So I will post you individually in Google Classroom. Everyone should prepare a PowerPoint or create a document or script in A4 sized paper and submit in Google Classroom for assignment. Any doubts on this? Everyone go to chat box. You can see an attendance link. Fill the attendance link and await. I'll give you another instruction also. Everyone go to chat box. You will get an form. If you fill the feedback, if you fill the form, you will be getting attendance. After filling, do not leave the meeting. I have an special instructions for you all. I'll give you 5 minutes of time, 5 to 10 minutes of time. Fill the feedback soon. So any doubts or questions? So in Google Classroom, you can check that Unit 1's material is available, and just now I had posted you Unit 2 material. You can have a view, Unit 1 and Unit 2. All the materials will be shared only through Google Classroom. After completion of each unit, I will be sharing its material. Still, only 12 members had completed their attendance. Still awaiting for them only. Those who haven't completed attendance, fill it. Still some 6 or 7 members has to complete the attendance, waiting for them. Then I'll give you the instructions. Still 2 or 3 members has to complete. Okay, uh, I leave it up to them. If they fill the form, they'll be given attendance or no attendance for them. Okay, the important instruction is that uh, regarding the first internal exam, which is to be scheduled on next week for you. I think hope everyone would have received the timetable. Has everyone received the timetable? Anyone can put in the chat box. Have you received the first internal test schedule? So according to the first internal schedule, our GPS Global Positioning System exam falls on 21, which is coming Monday. The portion for that is Unit 1 completely. Mode of exam will be completely using exam.net. So make sure you are having good internet. If you have good internet, you should upload the papers in exam.net only. Okay. Portion is Unit 1, Part B questions. You'll be having 3 Part B questions, maximum of 30 marks. So prepare accordingly. Thank you. You can pass on this information to the others. College reopening, as whenever we get instructions from Government of India, probably after November, maybe in the November or end of October or so. You'll get all the informations, don't worry. Thank you all. You can leave the meeting. Any other questions?